Alright, in this section, I'm going to be dealing with average current mode control. Essentially what this means is you're actually controlling the current through the inductor. Instead of controlling either the output voltage or the output current, you're basically controlling the current through the inductor. And what that entails is you have a double loop. It can also be called double loop control. And what you get in double loop control is an outer voltage loop that makes a current reference for the inner current loop. And this really presents a lot of advantages for converters because you can essentially ensure that your converter is constantly operating in CCM, in continuous conduction mode. Um, Additionally, you can actually save your MOSFETs. You can save your MOSFETs a lot of stress because inherently you are limiting the amount of current that goes through your inductor and by proxy your MOSFETs and your diodes as well. Essentially, the amount of current that goes through your converter. So you're basically limiting it on every cycle as opposed to having to check in the other methods sort of output voltage to duty cycle or output current to duty cycle where you're just controlling them like single loop control. If you want to limit the current, you essentially have to either use the duty cycle method where you sort of keeping fingers crossed in a way, or literally have another if statement to say if this is above this, reduce the duty cycle as follows, as opposed to double loop control where inherently it just limits the current by default, um, as long as your ADC works, of course. Um, so so basically in this video, I'm gonna in this particular section, I'm gonna dive straight into um the practical implementation of this. I sort of don't want to go into the theoretical because in the theoretical realm for average current mode control, it could get rather complicated, and it could get sort of tiring in a way, and I sort of want to go the other approach, the approach of this could be implemented, with patience and a willingness to sort of, you know, just go through it basically, going through selecting various coefficients to see what works, etc. It could be quite rewarding. Of course, calculating it will be rewarding as well, but you know, it gets daunting at times. The calculations for this specifically. So, um, like I said in this section, I'm just gonna dive straight into it, implementing it in firmware. Average current mode control, and I just sort of brushed up, stated loosely some of the advantages, but personally, I think average current mode control is quite cool. So yeah, here it is. Um, so for starters, and I'm gonna make a variable here called int loop count. So essentially, what you're doing in this case is, oh man, what did I do? Okay, so essentially, what you're doing in this case is you have two loops, which essentially indicates double loop control. So you have an outer voltage loop which is quite slow. So um for every time the outer voltage loop is executed, the current loop is executed 10 times. So the voltage loop executes once every 10 iterations of the current loop. I'll show you what that means just now. So first up, you want to go to the custom.h and you want to define the function that you would require in this case. So the functions are, first one is void just get it back here. So the first one is void dub loop So basically what this would be, it will be where the double loop will be implemented, of course. Okay, and here double loop voltage. And next we'll have double loop current. All right, and yeah, that's about it. So essentially, this will contain the entire double loop um, function. This will be for the voltage, and this would be for the current. All right, so let me just copy that and take that to custom. Oh yeah, so I already defined. So under custom, you want to include loop count as well. Extern int loop count, of course, is defined in the main function. So here, let me just do this. Okay. All right. So this is essentially what I'm talking about. So first off, the first thing you want to do is in the double loop system, you wanna increment the loop count variable. That's the first thing. That's the first step. And next, you want to check if loop CNT is equals to 10. What do? You implement, you first off, you zero out loop count. You make it 0 again. And then you implement, you call the function double loop voltage. So this is double loop voltage control function. And then but right at the bottom, you always implement double loop current every time this function is called. So in essence, the control frequency, the control loop frequency of the current loop is 10 times more than that of the voltage loop, essentially, because of this variable. So once you come in, it will only execute this once that value is equals to 10, and then it will zero it out, implement it, etc., and so forth. And yeah, that's about that. And to implement the double loop for the current essentially stays the same, the way it was before. It's basically, what I mean is this function is identical to this function, but this function is slightly different to this one. So that's what we'll be touching on now. So I'm just gonna go there, of course, because it's already there. I'm just gonna copy it, copy all of it, and paste that. Like I stated earlier, the output of this function is the iref, right? It's the reference that's actually used for the double loop current function. So after you implement this, after this is implemented, what you basically do after that, you want to state iref is going to be equals to iref max multiplied by the output here, by the outcome here. Right, and that's what's going to be. And then iref max is, of course, the maximum current reference that you require. So essentially what this is the maximum inductor current that you want. So this is where the inherent limit comes from. So whatever you state here, it will never get above that value. So let's just go there and define this. Okay. Okay. Let's change this to iref max. Okay. And in this case, the rated value is 2.133. And YV max, this is where everything becomes slightly modified. So here I'll change this value to 1.0. that value is going to be 1.0. All right. So in the double loop variety, let me just change this. Yeah, everything is supposed to be changed, has been changed over there. Okay. Yeah, lastly, the coefficients. You can try using this coefficient, but I'll show you now on the output. It fluctuates quite a bit. You might want to change it, but we'll just give it a try anyway, the way it is. And anyway, so that's the double loop voltage. So it's normal. It's just now you have to change this IRF max. Will be multiplied by that. That value maximum is 1.0 at this point, and essentially the output of this is going to be the IRF, the reference current for the current loop. So you have an outer voltage loop and an inner current loop. All right. So double loop current, and just go there to control current there. And it's exact same as this one actually. So there's like literally no difference there. Because this is what you're gonna be getting in the output. What you want in the output anyway. You want the reference which you actually obtained from the double loop voltage. And what this means is it basically keeps the inductor current in CCM constantly. It keeps the current in the inductor literally constant, which is fantastic. And that's that. And of course, this is the function you want to call now every 100 microseconds. And just go to the main code, time elapsed. You want to implement that there. Okay, just run this, see if we get any errors. No errors. Just go back, just ensure everything is nice and tidy. Okay, fantastic. All right, so I'm just gonna try it out now. Gonna literally implement this code and control it. Literally all the changes this value here, because the inner current loop you want it to be 1.0 times 2.133, or you can leave it as 0.75, but then you have to increase this value so that the maximum value is 2.133. Yeah, so this is the RF max. And all right, let me just write that code into the controller. And something I forgot to state was, if we go to the main function, we go to look at the private variables. So here, it says 1.2, but you want to start the IRF, because remember the IRF is going to run for 10 cycles before the current loop. Let me just go there so I'm not just talking nonsense. So this loop, this function dub loop current is going to execute 10 times at first on startup before this code. So you want to make sure there's a adequate IRF there that's not too high. So that's why I set up the initial IRF to be 0.2. And this value, well, that's 0.0 initially anyway. You want to set the initials to 0.0 until this executes. Well, you want to set the IRF to 0.2 until it gets updated by this particular function over there. So you want to make sure that that's the case. That's why to start off, we'll make that value 0.2. So I'm going to run it again. And of course, the VREF set point is 10.0 in this case. And just keep in mind, it's not controlling, it's not modifying the duty cycle directly as a result of the sensed output voltage. It takes that, gets a reference, generates a reference value from that value, from the output voltage, reference current value, and then the reference current value is what's used to actually modify the duty cycle directly. So it's almost like indirect control, if you will, not direct control. Just check the system here first. Um, so I just need to change the view over here so you can actually see what's happening. Let's go back to the custom. Okay. Flash. All right. So when I turn it on, as you can see, it's not constant, like almost like when we controlling the output voltage directly. It's not so constant, it fluctuates a bit. Let me just modify that there. As you can see, it's not totally constant. It's jumping up and down just a little bit because of the tight control that's happening. If you want it to be a lot smoother, you'd have to sort of change the coefficients to align with it. But if we actually take a look at the inductor current, which unfortunately cannot be done in this case because there isn't a current probe. But if one takes a look at the inductor current, one will actually find out that it's actually very it's continuous. It's in CCM, which is fantastic. I can't, yeah, I'm just gonna keep saying it's fantastic. But now I'm literally gonna in the code change the set point to a different value. Um, let's let's do it. Okay. Oh, and keep in mind in this case, the only set point we actually change is the what do you say, the voltage, the Vref. We don't change the Iref manually. The Iref is changed automatically and dynamically, um, based on what the Vref is gonna be. Okay, let me take it back to the other view. I just changed the to 15. Right. Um, of course, there's that offset, so you should expect something like 16 volts on the oscilloscope. Yeah, there we go, 16.3, 6.9 volts. So that's about it. So this is basically average current mode control. Like I said, it's very useful. Um, it holds a lot of uses and a lot of applications. I can't I literally cannot sing the praises enough of average current mode control because of its use cases. Um, for battery chargers, it's very useful there. For bulk in the bulk state specifically. Of course, you cannot use average current mode control if you're not operating in continuous conduction mode. That would sort of be a mess, you know. If the inductor is not large enough, that's one thing to be cognizant of. That it is operating in CCM for the most part. But anyway, that said, I think I'm gonna take it up to the rated, um, or close to the rated anyway, because the max value is 2.133, so it won't exactly get there, but to the 2.133 value, but it will get close, which is essentially what I want. So let's just do this and have the last set point selected. Okay, I'll go back to the main.c. So the last set point to select will be 16. Let's say, yeah, 16. And let me go back to custom.c. Modify the max value. Let's make it 2.2. Modify the IRF max slightly so that it gets to 2.133. Um, right. All right. Let me go back to the view that matters. Okay, turn it on. Right. All right. So let's turn it on. Right, there we go. 16 volts approximately. Well, of course, the oscilloscope has its little offset, so it's probably like 16.4 volts now. Yeah, that's it. That's the implementation of average current mode control. And of course, I have to speak of the elephant in the room, which is the switching, which is the switching noise visible. Um, Honestly, it's more of a thing with the source. I'm using an AC/DC converter. Um, for better performance in the output, the linear power supply would have been fantastic to serve as the input, but I'm using an AC/DC and sort of something that's very much available. Actually, an LED power supply, but I sort of connected that as the input, and the switch noise is just sort of propagating through everything, so it's kind of a mess there. But otherwise, the controller is operating. So that's basically it in terms of digital control of power electronic converters. Specifically in this scenario, the buck converter. So this is essentially average current mode control. Again, I literally cannot sing the praises enough of average current mode control. I mean, its use cases extend to far beyond what I could sort of think of right now. It's just it's just so advantageous to control the current through the inductor. It's so advantageous for longevity of the converter. It's for basically you're taking care of the components in the process. Um, you're keeping the system in CCM. I think that's the main thing, of course, to just sort of have the system last very long. And yeah, I would say, you know, I would say this is about it. Um, so in this case, I sort of wish you the best in all your applications with this specifically. And just turn this off. Um, Let me go back to the in your applications of this. Of course, everything stays the same pretty much. All you need to add is the loop count, and of course in the custom you need these three functions: the double loop voltage, double loop current, which are the exact same as the normal control. All you have to be cognizant of is that the output of the outer loop, which is the voltage loop in this case, is RF max. Is what the output of that is going to be the current reference, which is going to be RF max multiplied by the actual output. The RF max will determine the limit that you essentially put in on it. In this case, 2.2. Um, and the current loop, of course, will be different. And also, you might want to fiddle around with these coefficients a bit, because they are primed for single loop control, not double loop control. As you can see there, it was fluctuating just a little bit, but you can modify these coefficients to make it much smoother. Specifically, the 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 voltage one, you don't want it changing as much. Actually, if I just show that in this case, if you want it a lot smoother, you sort of want the voltage to be, a lot more stable. Okay, let's run. Yeah. Um, I just checked it over there. Um, I think it would help to have this like that as well. To reduce it, essentially what you're doing is you're increasing the settling time. What you're doing when you make the coefficients much smaller than they actually are, or what you actually calculated, you're reducing the settling time. And you actually have a much more stable output. I suppose I should probably show this now. Output of the system. Um, but not. As you can see there, the output is a lot more stable. It's not jumping up and down as much, in terms of like its fluctuations, etc. And okay, I'm just gonna change the coefficients again, make it more, just to show you what effects that will actually have on your system output. I'm gonna add another 0 here. Okay, change the coefficients and go back to it now. Let's do that. Okay, flash on, turn it on. You can see there's hardly any jumping up and down. It's sort of just stable on that same state. Well, the exception of the switching noises, etc. But everything pretty much is stable. Yeah, that's about it. That's about what you need to do in that case to make it more stable. Of course, taking into account everything else. It should be noted that these values can be calculated. There are calculations for these things. I just want to take everything back to its normal state. Yeah, that's it. And of course, using this code, you sort of gonna um shuttle between double loop control routine for voltage and control for current. I kind of feel like I'm just going on and on at this point. So I think this is about it. I wish you all the best in your applications of average current mode control. This is essentially it from a firmware perspective. From a basic perspective, anyway, there are other aspects involved in the code for like industrial applications, etc. But this is a very strong starting point for this, and this is essentially how to do it implemented with the STM32 microcontroller. You know, cheers. See you in the next one.